Hi. Hello, 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 hello. How we doing today? I hope that we're doing well. This is my sincerest hope and dream that we're all doing well. Hello, Astrologophones. Good to have you. Happy to have you. Glad to be here. Glad to be here to finally get to talk about interactions, which I love interactions. They're one of my favorite things in statistics. I'm very excited about it. I do have some unfortunate news. Doing good. Got an XXL shiny Thunderous Theory entirely. Dude, congrats! What the heck? That's awesome! Oh yeah, from the Pokemon Go rewards this morning, the ones that they gave everybody for screwing up, I got a shiny. What's it? It's a shiny. I can't remember the name of it. One of the legendaries. The bug-ish one. The bug with the jetpack. I got a shiny one of those, and it's a pretty good one. It's maxed out on attack and defense. Genesect, yeah. Or Genesect, I don't know. Either way, I got a shiny one of those, and it's maxed out on 2 out of 3 of its stats, so I'm pretty happy about it. I got really lucky. I'm very pleased. Uh, it is. It's a really good shiny. I'm quite fond of it. I was very happy to get it. I'm glad that happened because honestly, yesterday I didn't have a great day. Like, well, I mean, I was fine. Like emotionally, I was fine. I just had really bad luck. My commute was more than twice as long as usual due to sheer bad luck, and that was deeply unfortunate. And actually, I'm kind of having bad luck today. So when I tweeted about the stream, I said something along the lines of like, I hope we'll be talking about this in 20 minutes. And there's a reason for that. We'll see if I make it through this whole slideshow. So story. I came home from work and I was very hungry. And I made myself some food. And I've made this thing about 1 billion times, no problem, not an issue. And everything went according to plan this time as well. And then I started eating it. And like, it was fine. It was totally normal at first. And then there was a little bit of a weird taste in it. It tasted strange. It didn't taste right. But sometimes you are a very, very hungry, very, very tired person who doesn't have a lot of time and also hates wasting food and money. So you just keep eating it. You eat it, you ignore the taste, you eat the whole thing. And now, calling them stabbing pains wouldn't be correct, because knives are much bigger. But like, hi Ray, welcome. I guess I could call them stabbing pains if you imagine a needle instead of a knife. So that's currently where we're at. I'm hoping it's nothing. We're just gonna power through it. But if you stop hearing from me, if you stop hearing from me, if I suddenly end the stream, just, I don't know, contact Psy. Just tell Psy something's wrong. I know she's probably asleep right now, but when she sees it in the morning, she might be able to find somebody who can help me. It's probably fine. It's probably fine. Don't be like me. Don't 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 do what I just did. It was a horrible idea. I knew it was a horrible idea as it was happening. As I was eating the thing, I'm like, I should stop eating this. I should really just stop eating this. And then I didn't. I didn't because I was hungry and I didn't want to waste food. Because that would be a waste of money. And I didn't have much time to eat. Foolish. foolish. Anyway. Okay, so yeah, if we end early today, I am sorry. Yeah, hopefully it's fine. Hopefully, like I've had stomach things like this before, and all of them were fine. Maybe I don't know if this is the same, but I'll probably be fine. I've been through worse, I'm sure. Probably. And if I'm not fine, then I'm sure that Psy could find a way to get in touch with somebody who could break into my apartment and find my corpse. Maybe. I don't know. I doubt it will come to that. It definitely won't. It almost certainly will not come to that. It should be all right. Anyway, let's talk about Factorial ANOVA today. This is more important. This is frankly more important. Factorial ANOVA is love and life. This will heal me. I know it. I know it. This will fix me. All right, so previously. So a bit of review. I'm going to ask some questions to review. We've been talking about ANOVAs for like the past few lectures. The past 3. Science will fix me? Yes. And for me, statistics will fix me as well. Science will also fix me, I imagine. But statistics in particular will absolutely fix me. So, if we reject the null on an ANOVA, what does that tell us? What have we learned? What have we learned? I guess lecture 3, last 3, 12, 13, and 13 again. No, look, I've been really bad about naming my files. But I think I got them right? I think I at least got the video titles right. The lecture slides, probably not, but the video titles should be fine. Right? It's all ANOVA, you know? It's all ANOVA. Now I'm going to check. I need to know. Wait, it's 12, 12, and 13. What have I done? Horrible mistakes were made. I'll fix it. I'll fix it eventually. I'm not gonna worry about it. It's fine. It's whatever. Who cares? Not me. I care a little bit, but not enough to fix it right now. Oh, man. Anyway, if I reject the null on an ANOVA, what have we learned? What does that tell us? If it's significant, there is a difference. There's some non-error difference between at least 2 samples. Correct. At least 2 of our groups are different from one another, above and beyond sampling error. All right, so you've rejected the null. Now you have to follow it up. You have to follow up your ANOVA to find out exactly how many differences there are and where those differences are. One way to follow up an ANOVA is a planned contrast. Anyone remember when we use a planned contrast to follow up an ANOVA? My hair is falling in my eyes. Okay, there we go. I need a headband or something. When you already have an idea of where the difference is, exactly, Hair Day. And welcome, Hair Day. Happy to have you. Good job. All right. When do we do post hoc tests? When would I follow up an ANOVA with a post hoc test? When not that. That is correct. When not that. Yeah. When we do not have any clear expectations for where the difference is. Yeah. Mm-hmm. Basically, when we did the ANOVA just to see what would shake out, we didn't have any clear idea of what we would find. This one is a bit... I feel bad asking this when, like, I don't have a full lecture hall of people to bother with it, but... Anyone want to give me a guess for what the degrees of freedom between for a planned contrast would be? I know it's been a minute. It's been a minute since we talked about this. Number of groups minus one. Correct, correct. And how many groups are you comparing in a single planned contrast? Two, correct. So the degrees of freedom between for a planned contrast would be one. You're comparing two groups. It's the number of groups minus one. So for a planned contrast, the degrees of freedom between would always be one. I'm sorry, I just spilled water all over myself. Oh, I just, some days are like that. Oh, F you. But none of it got on the, oh, some got on my tablet. I was gonna say none of it got on the technology. It's okay. It got on my tablet, but not the part of my tablet that has any access to the internal electronics, so we're good. Safe. Okay. Can anyone remind me what the term experiment-wise error refers to? Sorry, I've got Deco 27's new song stuck in my head, and I know that's not how you pronounce his name. It's like Deco Nijunana or something, but the chance overall that you get a false positive across all tests? Yes! Yes, Astrolatrophos. Errors from experimentation sampling, not the real difference. Yeah, it's close to that. Yeah, it's the probability of that. Water and I, lucky this isn't a quiz because I was still absent for these topics. I would have flunked. I mean, if you knew that there was a quiz, you probably would have studied, right? Deco, I love doing art from them. Yeah, Deco has a lot of fun. I've been thinking of doing like art based on some of his songs. I thought my urge to get V-Theorem to do a cover of a song is still very high, and I would like, if I had more resources and knowledge of mixing music and stuff, I'd absolutely do a cover of his new song, Telepathy. You did Rabbit Hole? Nice, I'll have to listen to that. That is such a freaking catchy song. I've had it on loop for a long time. And today, though, I had Telepathy on loop, so it's stuck in my head. Okay, anyway. How do we protect ourselves from experiment-wise error? So if experiment-wise error is our total chance of making a type 1 error across all the tests we do, how do we keep that number down? How do we keep our experiment-wise error low? And there's a bunch of different answers to this question, by the way. There are many correct answers. There's many ways to do this. All I want is one. Is it the Italian guy? Turkey test? Oh yeah, Schiffe or Tukey. Yes, those two, both of those are post hoc tests, and by doing post hoc tests, that is absolutely, both of those are ways that we can keep our type 1 error down. Yes, post hoc tests are more, yeah, exactly. Both of those fall under that category that Astrolatrophos just pointed out, getting more strict about when you reject the null. Both Schiffe and Tukey are more strict about rejecting the null, so they're less likely to produce a type 1 error. So both of those things are correct. All three of you are right. I'm assuming, Water Knight, that by the Italian guy, you're referring to like Schiffe or Tukey. I'm not sure which, because I don't know enough about Italian names, but... and I don't know enough about those two people to actually know for sure. I should look into that. Anyway, good job, everyone. We are done with our review. Now we can get into the fun stuff. The stuff that I've been looking forward to. This is one of my favorite things to talk about in the entire, like, all of the stats stuff that I talk about. So I'm very excited. So, up until now, every test that I've talked about so far, you only had one independent variable. You only had one thing that was differences between conditions that separated out your conditions. But a lot of the time, the real world's a lot more complicated than that, right? A lot of the time, you want more than one independent variable. You want to account for more than one thing. Today, we are talking about Factorial ANOVA. We are talking about Factorial ANOVA, which allows us to use more than one independent variable. We can account for more than one thing. Oh, I'm so excited. Factorial, by the way, we talked about this in Intro to ANOVA, but factors, like the name that we use for categorical independent variables, like the ones you have in ANOVA, it's called a factorial ANOVA because it has multiple factors, multiple independent variables. Oh man. Sorry, I'm excited. I'm like, I can't believe I've reached the point in my life where I have favorite statistical tests. This isn't my favorite statistical test, but it's the closest we're gonna get in this series of lectures to my favorite statistical test. Factorial? Is it linked to the exclamation point factorial? I don't believe so. I think this is a different type of factor that we're talking about here. But as you know, I have zero recollection of that level of math, so I can't say for sure, but I'm pretty sure that this is completely unrelated, because in this case, factorial refers to factor as in a categorical independent variable, which I'm pretty sure is completely unrelated to factorials. But I'm not an expert on mathy stuff, so I could be wrong. But pretty sure it's a different thing entirely. Pretty sure. Unless you're just trying to jump scare me talking about factorials, in which case, why are you evil? Why do you do this to me? Is it because it's entertaining? In that case, valid. I will not begrudge you that. All right, anyway. So let's start talking about interactions. Once you have more than one independent variable, you can start playing with these things called interactions, which are my favorite thing in statistics. I love interactions so much. Oh my God. Okay, anyway. Usually, but this time it was a genuine question. That's fair. Yeah, I'll have to look it up, but I'm pretty sure that those things are unrelated, or if they are related, their name is not a reflection of that. Anyway, so I don't know how many of you have watched The Apothecary Diaries. I love The Apothecary Diaries. It is my current favorite anime airing right now. I've been reading the novels. Good stuff. So I figured I'd use it for an example here. In episode 14 of The Apothecary Diaries, our protagonist, Mao Mao, she's not so much tasked with figuring out why a storage warehouse exploded as she just decides she's gonna find out why it exploded. And the answer is an interaction, so I figured I'd use that as an example. So, we have two independent variables here. The first one is flour. So what she does is she gets a wooden box, and the first thing that she puts in the wooden box, and the wooden box represents the warehouse. Our first condition is flour. And it has two levels. Our first factor is flour. It has two levels. One level, there's no flour in the box. And our second level is there is flour in the box. So independent variable 1, 2 conditions, no flour or flour. Or to put it in ANOVA terms, factor A with two levels, no flour and flour. This is cooking flour, if that wasn't clear. Then we have our second independent variable. This is our source of fire. Dust explosion. Oof, yeah, Harrowday sees exactly where this is going. I don't know if you've seen the show, but even if you haven't seen the show, you knew exactly where this was headed. This is heading towards a dust explosion. Chaffee was German-American and Tukey seemingly a generic white American from Massachusetts on his wiki page. Sounds about right. Thank you for looking that up. You've saved me a wiki walk for later tonight. Anyway, yes, our second independent variable is no fire. It is whether there is a fire source. Levels are no fire and fire. Now, for our first independent variable, the effect of flour is nothing. You put flour in the box, there's no obvious difference between flour in the box and no flour in the box. Nothing changes. Hey, Maury! Yeah, you do know this guy. I dragged you into this series, you poor soul. So, first independent variable, nothing. Does nothing on its own. Our second independent variable, fire source, the box with no fire, nothing special happens. If you put fire in there, this box starts to smoke a bit, but nothing notable happens. Do you like the smoke that I drew in here? So yeah, nothing notable happens. But that's not the entire story, right? Harrowday has already guessed where this is going, and I know Maury has seen this episode, so Maury also knows where this is going. It's not just the effect of fire on its own or the effect of flour on its own. We're not just looking at fire versus no fire and flour versus no flour. We want to look at the combinations because something interesting might be happening in how those two variables combine. And yeah, Harrowday already knows where this is going. The nice thing about Factorial ANOVA is that we can learn 3 things from a single ANOVA. The first we can learn is the effect of flour on its own. Just putting flour in the box, what does that do? And we've kind of established that doesn't seem to do anything. The second independent variable on its own, we can also test that. We can see what fire does on its own relative to no fire. And in this case, it looks like it makes the box start smoking a bit. But we can also do a third thing. We can look what happens when you combine the flour and the fire. So I can get the effects of flour versus no flour, the effects of fire versus no fire, and I can get the effects of the combination of flour and fire. All 3 of these things from a single statistical test. How cool is that? All of these things all at once. I'm testing essentially 3 hypotheses at once. I'm sorry I keep winking and blinking at you. I need to tie my feathers out of my face, and I don't have anything on me to do that right now, unfortunately. Okay, so here's factor A. This is whether there's flour or not. So collapsing across factor B, we are ignoring whether there is any fire or not. We're only looking at if there's flour in the box or no flour in the box. We see nothing. Nothing happens to the box. There's no notable change in the box, just depending on whether there's flour or not in it. Then we can look at factor B, ignoring factor A, collapsing across factor A, ignoring whether there's flour in the box, just based alone on whether there is a fire source or no fire source. The box smokes when there's a fire source, doesn't smoke when there's no fire source. So factor A on its own, flour on its own does nothing. Factor B on its own, it smokes when there's fire, it doesn't smoke when there's no fire. Those are their individual effects. And if we just added those together, if I just took the effect of flour, which is nothing, and the effect of fire, which is smoke, and added them together, essentially you just expect the box to smoke if I combined flour and fire. But again, it's not just about what these 2 things do on their own, it's about what's happening when you combine them. What's happening in these individual combinations of flour and fire? That's the big question here. That's where the fun bit comes in. What happens when you have a bunch of flour dust in an enclosed space and introduce fire? And I know Haraday's already answered this, but yeah, what happens when you have a bunch of flour dust in an enclosed space and introduce a flame source? What happens? Anyone know? I'm sorry, I know that you have already said this, but I just want to check in before I show this picture. It feels important for like narrative pacing or something. It can explode, and that's exactly what happened here. So the point here is that if we just took the effect of flour on its own and the effect of fire on its own, we would just expect a little smoke. But that's not true. When you combine those 2 things, they did something different together than we would have gotten just by adding together their separate effects. We got a much bigger change to the state of the box than if we just added together flour's effect and fire's effect. That's an interaction. It's not the only type of interaction, but that is a type of interaction. When these 2 independent variables are together, they do something different than what they would have done if you just took their separate effects. And that's why I love interactions. They are so cool. They're so neat and interesting to me. I love interactions so much. I don't know if that's sad. Some other examples, again, sort of like anime-ish stuff, because, you know, that's kind of my thing. Other examples of interactions, pilots and mechs. Let's say I have you fight an alien spaceship. A pilot on their own probably can't do much to damage it. A mech on its own can't move without the pilot, but when you put them together, they can do a lot more. A shonen protagonist on their own can probably do some decent damage to the antagonist. The power of friendship on its own doesn't really do anything, but when you combine them, the shonen protagonist will get a huge power-up. But it's not always like one thing amplifying the effects of the other, right? It's not always like flour dust amplifying the effects of smoke, or a mech amplifying the damage of the pilot, or whatever. Sometimes it can be like things like dampening the effects or reversing the effects. So for example, another interaction, I'm sorry, there's no Bravern pick. Clearly they should be. There should be, but Bravern can kind of do stuff on his own, you know? So I felt like that wouldn't be a good example. I was thinking kind of Gundam-y, because I think Gundam pilots, Gundams can't really operate autonomously, right? I think. I've never actually watched a Gundam series. That's my embarrassing confession. I don't like most mecha. I'm sorry. But some mecha get a pass, like Star Driver and Bravern. I think it depends on the series for Gundam. Yeah, that's fair. I've heard good thing. I know that they can vary wildly. Anyway, but another type of interaction, sorry, I don't want to get too off track, is poison and antidotes. On its own, poison will make you feel horrible. On its own, ideally, like, depending on the antidote, it may or may not do anything. So you'd think if you just added the effects of poison and antidote together, you'd just feel horrible. But no. When you combine the poison and its antidote, the antidote will diminish the effects of the poison, right? Maybe not cancel it out, but, you know, it'll at least diminish the effects of the poison. So interactions don't necessarily always mean one thing is amplifying the other. It could be one thing is canceling out the other, or one thing completely flips what the other thing does. There's a lot of different ways you can have an interaction. But essentially, the gist of it is one independent variable changes what the other independent variable does. One independent variable is affecting what the other independent variable does to your dependent variable. So the pilot is changing how much damage the mech can do. The power of friendship is changing how much damage the shonen protagonist can do. The antidote is changing the poison's effectiveness. An interaction, one independent variable is changing what the other independent variable does. Basically, the independent variables do something different together than if you had just added their separate effects. That's an interaction. It's kind of hard to put into words. It's not necessarily they're greater than the sum of their parts, but the combination of the independent variables is different than the sum of their individual parts. Does that make sense? How we feeling? Is this making sense? They do something different together than they would have if we just took their separate effects? Hi, Bushi! Welcome! Oh boy, traffic jam on my commute to practice. Perfect excuse to hop on. Welcome! We're talking about Factorial ANOVA and interactions. Oh yeah, this seems intuitive. Good, because this is something that I think a lot of people tend to struggle with, but I think for this presentation, I've changed a little bit about how I talk about it, and I'm hoping that's made it easier to easier to comprehend. So maybe I mean, I know that the people in this audience are not the same people as the kind of audience that I have in my classroom, but maybe I should start incorporating this method of explaining it there as well. Anyway, so we are still talking about an ANOVA at the end of the day. This is a specific type of ANOVA that can test for this kind of stuff. I'm only going to be talking about a two-way factorial ANOVA today for the sake of simplicity. Two-way factorial ANOVA is a factorial ANOVA, or an ANOVA with two independent variables. But you could also have three independent variables. That would be a three-way ANOVA, or four independent variables. That would be a four-way ANOVA. So we're going to stick to two-way ANOVA, but you don't need to stick to just two independent variables. You can add more. To be frank, I do science stuff. Not acting exactly as sums is pretty typical. Yeah, exactly, right? Right? Yeah, like I think that this is, like, you encounter this stuff a lot in science. I think this is a pretty standard thing that you can expect to encounter in a lot of different areas of science, which makes me happy because I love it. I love it. I mean, the world is too complicated to be drilled down to just two conditions or, like, you know, just one independent variable. I think, and also it's just fun to see how things interact. Maybe I should have done more chemistry. I don't know, but I think it's fun. I really enjoy it, and it helps you account for more than you would be able to otherwise. And it's just cool. It's just neat. I just think it's neat. Anyway, so we've been talking about ANOVAs so far, and we know ANOVAs split the total variability in your dependent variable, all the variance in scores in your dependent variable, into two pieces to start. That's the between subject, or well, the between treatments variance. That's the effect of your independent variable and some error in there. And then the within subjects variance, that is also just error. The factorial ANOVA, specifically the two-way one that we're talking about today, and we're going to keep it all between subjects. You can have within subjects variables in here, but for the sake of simplicity, I'm keeping it all between. The factorial ANOVA splits up the between treatments variance into three pieces. Variance due to your first independent variable, factor A. Variance due to your second independent variable, factor B. And then variance due to the interaction of your two independent variables. So in the repeated measures ANOVA split up your within subjects variance. This ANOVA is splitting up your between subjects variance. It's not interested in explaining away error right now, but it's interested in breaking down exactly which independent variables were accounting for how much of the variance. So we're still splitting up the variance, we're just doing it slightly differently than we did before. So I'm going to use an example from social psychology here, because social psychology is kind of that's my area. That's the type of psychologist I am. How many of you have heard of this phenomenon called social facilitation? Anyone heard of it? If you haven't heard of it, like, I think it's one of those things that you probably could, like, intuit. You probably do already have an understanding of this kind of thing. You might just not know the, like, jargony name for it. Hey, Xenotime, wait, can you use the variance due to A and B as a pseudo correlation thingy thing? You can, so this is all categorical variables. So technically not really. You could technically convert the effect size for your interaction into R squared, which you could convert into a correlation, but I don't know how useful that would be. But I think you might be thinking of regression. So technically ANOVA is a special type of regression, and I don't have a lecture on regression, unfortunately, which sucks because that's what I actually end up using the most in my work. But yeah, regression can also have continuous independent variables, and regressions have betas that are kind of similar to, like, pseudo correlation-y thingies, you could say. So you probably could treat it that way depending on the type of variables you're using, but in this case I probably wouldn't, because all your independent variables are categorical. Yeah, no, like, it's not like, I think you're onto something. I think that this particular thing isn't there, but there are many related concepts that I think do go along close to what you're saying, if that makes sense. Anyway, social facilitation. This is a phenomenon in social psychology, originally described by, I don't remember his first name, Triplet, though. What he did was he went out and he watched a bunch of people doing bicycle races, and then he wrote papers about it. I just remember his name being Triplet. I don't know. I think it's fun. It does, thanks. Oh, good. All right, so social facilitation is all about having an audience when you're doing something, having people watching you. Sometimes having an audience or having people cheering you on can be really helpful. Like, having people cheering for you can really push you to do your best in some situations. But in other situations, having an audience and people cheering you on might like put a lot of pressure on you, make you nervous, and make you do worse. Wait, that's sick. I want to watch people do bicycle races all day. Norman Triplet, that's the guy. Yeah, no, this is a long time. This is like in the 30s, in the 1930s, maybe? I don't remember exactly when Triplet was active, but I'm sure that you could try and replicate his work as an excuse to go watch some bicycle races. Anyway, so we're going to try and replicate social facilitation. Well, not really. We're going to use it as our example. Born in Illinois in 1861. Hey, Illinois, nice, 1861. Man, he's older than I thought. Norman Triplet was... When did Norman Triplet social facilitation? 1898! That's older than I thought. Good for him. There are 5 people in chat watching you lecture right now. You better not let us down the lecture's on. I am used to lecturing to many more people than 5, so I am not at all concerned. during the Victorian. Oh my God, don't put it that way. Actually, I wasn't alive then, so I guess I shouldn't be feeling old. It just feels weird. I'm used to most social psychological phenomenon being much more recent than that. So like social facilitation and triplet being from like the freaking 1800s is wild to me. Though I do know he was one of the first social psychologists, so I guess in that way it makes sense, but it's still weird to me. He's older than the t-test is what's getting to me. Triplet was running around. Triplet was born 40 years before the t-test was invented. That's what's screwing me up. He found social facilitation over a decade before the t-test was invented. That is what's really messing with my head right now. Anyway, so he died in 1934. So he hasn't been dead for a full century yet. It's fine. It's fine. I can mentally handle that. Surely. Surely. Wowzers. Yeah. Anyway, okay. So, sometimes having people cheering you on makes you do better. Sometimes it makes you do worse. And triplet was kind of like, well, why? Why does it help sometimes and why does it hurt sometimes? And I imagine quite a few of you are already kind of like, you probably have some pretty good guesses. I'm amazed the universe even existed before the t-test. Right? Right? I mean, like, I'm being sarcastic, but also, like, I'm constantly amazed by how recently the t-test was invented. It feels like it should be from, like, the 17 or 1800s, but really, it was, like, what, 1906 or something like that? Like, it feels like it should be older than it is, which is one of the things that, I don't know, time. Time is weird. I'm not going to think too hard about it. Let's talk about social facilitation. Okay. So, social facilitation, the social facilitation effect is actually an interaction. So let's say we're doing a study and we have participants randomly assigned to either complete a simple test, so they're doing addition problems like 1 + 1 or 2 + 2, or they do a difficult task. We're having them compute a whole bunch of independent means t-tests from scratch by hand on a whiteboard. And then there's another set of conditions. They're randomly assigned to either have people watching them do this or have nobody watching them do this. And our dependent variable is how many problems they get right. So we have two independent variables here. What is our first independent variable? As a physics major, I confirm time is weird. Yeah. 1908, so it's only 117 years old, just barely everyone who was alive when it was created by 1 year. It just barely, everyone here was alive. My brain can't parse this, I'm sorry. Yeah, it is weird though. It is weird for sure. Timey-wimey things. Right. So, can anyone tell me what one of the independent variable here is? Everyone alive at the time is dead, but only by 1 year is... Oh! Oh, that's what you meant. Yeah, yeah. That's wild. That's wild. There's officially no human overlap that we're aware of between the people alive today and triplet. Or, no, and the creation of the t-test. That is wild to me. That's scary. Anyway, right, okay. Can anyone tell me one of the independent variables here? What are the factors here in this study design? The task, yes. Was the task easy or was the task hard? That is one of our factors. Did you get an easy task or a hard task? What's the other one? What's the other independent variable? Onlookers, exactly, yes. Whether you have an audience or not. And finally, what's our dependent variable? How well you do, exactly. How many problems you get right, your performance. So essentially, we have a study design that looks a bit like this. We have our first problem solved correctly. Yes, both of you are correct. So we have our first independent variable, our first factor, which is whether you have an audience or not, yes or no, and the order doesn't really matter. I'm just saying first for the sake of simplicity, but the order doesn't matter. So we have one independent variable, one factor, that's whether you have an audience or not. You're doing this in public, you have an audience, or in private. We have another independent variable, that's how hard the task is. You're either doing a difficult task or an easy task. And then we have 4 possible combinations of these conditions. We have some people who are doing the hard task in public with an audience, or the easy task in public, or they're doing the hard task without an audience in private, or the easy task without an audience in private. Now, disclaimer for the rest of the lecture, for the sake of simplicity, I'm just going to pretend that sampling error does not exist for the rest of this lecture. We'll talk about how we deal with sampling error in this next time, but for now, we're just going to pretend sampling error is not a thing here, for the sake of keeping things simple while we explain this. Just warning you. Finally made it to practice, so I'll be hopping off. You probably don't need me to tell you this, but you're doing awesome. Have a great evening. Thanks so much, and I hope that practice goes well. You swing that sword. Go kick some butt. Or don't kick any butts, but, like, have fun. Have fun. Succeed. Triumph. Yes. All right. So, we've got 4 possible combinations of these, which means we have 4 separate means. We have the average number of problems solved correctly for hard problems in public, for hard problems in private, for easy problems in public, and easy problems in private. We have 4 means now. That's a lot. Now, I'm going to introduce you to something called a main effect. A main effect is the effect of only one of the independent variables on its own. So you can think of this as like, essentially we're doing a t-test, or we're doing an ANOVA or something like that on just with one independent variable. So for example, we might have an independent or a main effect of task difficulty. And that's whether people did better on the difficult task or on the easy task. And we have a main effect of having an audience, and that's whether people did better in public or in private. And this is more or less determined by something called the marginal means. These are means in the margin of this table. So it is the average number of problems people got right in public, ignoring how difficult the task was, and the average number of problems people got right in private, ignoring how difficult the task was. So averaging over task difficulty, people on average got 40 problems right in public, and on average got 40 problems right in private. There. Now I'm not blocking anything. Yeah, so this would be an indication probably that there's no main effect. Both public and private got an equal number of problems right on average. So if I just done a t-test only looking at whether somebody was doing this in public or in private, I wouldn't have found anything. That's my first main effect. I'm only looking at whether they have an audience or not. I do not care what type of task they were doing. We can also look at the main effect of task difficulty, so how difficult the task was, and this would be a main effect. I only care how hard the task was. I do not care whatsoever if they had an audience or not. So I'd use marginal means here. The average number of problems that people got right on hard tasks, averaging over, ignoring if they had an audience or not, was 35. And the average number of problems people got right of easy tasks, ignoring whether they had an audience or not, just averaging over that, was about 45. And again, remember, for now we're pretending sampling error doesn't exist. So this would suggest that people did better on the easy task than the hard task, which is good. We want the easy task to be easier, so it's good that people are doing better on the easy task than the hard task. Those are our first 2 things, and we'll talk about the math of how you do this later on, next class. But for now, like, the marginal means, the means of each row, indicate whether you have an effect of your first independent variable. The means of each column indicate whether you have an effect of your second independent variable. So those are the independent variables on their own. Those are the main effects. But we also have the cell means. So inside this matrix, in all these combinations, these are the ones that you use to determine if there's an interaction. The main effects, the effects of each independent variable on their own, are determined by these marginal means. If there's an interaction, is determined by the means in the cells. These are called cells. The individual combinations of our two independent variables are called cells. We have 4 cells here, 4 possible combinations of our conditions. So now let's talk about interactions a bit more. So again, another way of defining interaction. An interaction effect is when the effect of one factor or independent variable on the dependent variable differs depending on the level of the other independent variable. So one independent variable is changing what the other independent variable does to the dependent variable. So for example, in this particular case, social facilitation. So the social facilitation effect finds that people do better on easy tasks when they're in public relative to private, but they do worse on hard tasks in public relative to private. Depending on if they have an audience or not, the effect flips. In other words, the effect of having an audience depends on the difficulty of the task. Marlon, welcome! The hard and easy having the same score in private seems conspicuous, but I assume this is an example where the numbers popped out of thin air. Exactly. It's the numbers popped out of thin air, and for now we're pretending that sampling error doesn't exist. Yeah. Just for the sake of simplicity. But yeah, these are numbers that I just made up, you know, like they don't actually reflect real data. And we're pretending that these are perfectly, precisely correct numbers with no error whatsoever. So, to answer whether there's an interaction here, we need to look at whether the effect of one independent variable depends on the other. There's a couple ways we can look at this. We could frame it as, does the effect of having an audience change depending on whether you're doing something easy or difficult? Or we could think of, does the effect of the difficulty of the problem change depending on the audience? Both ways of thinking about it work, just whichever makes more sense to you. This right now is framing it in terms of, does the effect of an audience depend on whether you're doing an easy or hard task, which is typically how social facilitation is thought of. It's typically framed that way, though technically you could go the other way too. We see that when you remove the audience when you're doing a hard task, you solve 10 more problems. But when you remove the audience when doing an easy task, you solve 10 less problems. So 30 minus 40 is negative 10 here. 50 minus 40 is positive 10 here. The difference changes. This is the best way I know how to explain an interaction, but the wording of it is horrible. The difference is different. The differences are different. In one case, removing the audience helps your performance, but in the other case, removing the audience hurts your performance. Myelin is that good at psychology. They just make up numbers out of thin air and they turn out to be exactly right with no sampling error. I know, right? Aren't I a genius? Oh man, if only it worked that way. That would be incredible. So the idea here is that if the differences in cells are different, if the change from an audience in the hard task is different from the change for the easy task, that indicates there's an interaction. I mean, I had a chance of that happening as non-zero. That's true. Oh, wait, that makes sense. Okay. So people tend to do better. This is social facilitation. People do better on an easy task in public, presumably because they're already confident in it, and then having an audience makes them want to push themselves to do even better. But they do worse on a hard task in public, probably because they're not very good at it and they feel very pressured. So this is what Triplett was observing in bicycle races. He noticed that professional bike racers were getting faster times when people were watching them than when they were practicing with few to no people watching them. And that's how he came up with this idea that social facilitation might be a thing. And I'm sure that you've encountered this as well in your lifetimes, whether it's doing better when you have an audience, or doing on something that you're good at or that you've practiced a lot, or doing worse when you have an audience on something that you're bad at or haven't practiced a lot. Psychology probably does not work that way. No, it doesn't, unfortunately, but stats lectures can work that way because I'm making up hypothetical situations to make things way easier to understand than they would be if we jumped straight into the real messy data. I want to make sure that the general concept is there. Apparently he spelled it sports. He specialized in sports and magic, apparently. Yeah. Case examples, yeah. Rather than case examples, I'm using fake data here, but maybe one day we could do case examples. That would be fun as well. I have in the past collected data from my students and then had us analyze our own data, and students seem to like that. So maybe we could do that as a stream sometime as well. I would like to do that. That might be what we do next. Maybe after this series of stats lectures is over, I could just collect a big data set from Twitter, and then we can go through each type of statistical test that we've talked about together and analyze it based on that, with that real data. That would be fun. Okay, anyway. You can also do this the other way. So this was just like looking at, does changing the task difficulty affect what audiences do? This is framing it the other way. Does changing having an audience affect what task difficulty does? We can also do it this way. You can do it either way. They should both tell you yes if you have an interaction or no if you, they should give you the same answer. But in this case, I noticed that moving to an easy task in public increases my performance by 20 points. So 30 minus 50 is negative 20. But if I change to an easy task in private, it doesn't actually help my performance whatsoever. In private, it doesn't matter how difficult the task is, I'm doing the same. But in public, the difficulty of the task matters a lot. It makes a big change. This indicates that there is an interaction. There's a big change in public, but there's no change in private. The difference between that difficulty makes is different depending on whether you're in public or in private. The differences are different. I hate explaining it that way, but I don't know how else to put it. The differences are different. They're different. It does a different thing. So if you're determining if there's an interaction, just always make sure you're going the same direction. So like if I went public to private for hard tasks, I would want to do it in the same direction for easy tasks. Like if I'm going top to bottom, top minus bottom, I want to just make sure I'm being consistent. Or if I'm going left to right and then left to right, just keep it consistent. You can do rows, you can do columns, but always make sure you're starting at the same place and then subtracting the same thing. If you switch, you might miss an interaction that is there, or you might think there's an interaction that's there when there isn't one. So just be careful about that. Only look at the rows or the columns. You don't need to look at both. It's redundant. They'll give you the same answer. Now, let's talk about interactions in graphs. And this is what screws me up. Okay, so when I was doing that collab with Phi a few months back, where we read that paper, it was looking at exercise and diet on anxiety. And that was a question about an interaction. The hypothesis, what they were asking was an interaction, but they weren't testing it like an interaction, and then they weren't graphing it the way us psychologists would typically graph an interaction. So it took me a long time to figure out what was going on there, because apparently biologists and psychologists graph this kind of data differently. So I'm going to teach you how psychologists would graph this stuff. But if you want to know how biologists graph this stuff, go ask Phi. We've had long conversations about which is better, and I think we established it depends on our goals. It seems like biologists, or at least the ones that do the kind of stuff that Phi does, are more concerned with being able to see the main effects on the graphs, whereas psychologists are more concerned with being able to see the interaction on the graph, which affects how we organize the graph. Anyway, here's the data from that social facilitation study. On the left, we have the means for questions solved in public. On the right, we have questions solved in private. Is the way information is presented across scientific disciplines within the domain of psychology? Yeah, that would probably fall under metascience or semiotics. I don't know if it'd be semiotics, because I'm not actually too familiar with what's, like, I'm aware that semiotics is a thing, but I don't really know what it is. Semiotics. The study of signs and symbols and their use and interpretation. Yeah, that might fall under semiotics. I bet it would be like, you could probably study this from like a communication viewpoint, and that would we'd probably call that they'd probably call that semiotics. For us, in psychology, we would refer to this as metascience. But yeah, it is interesting how different disciplines display their data and how that shows different goals and priorities in terms of like what they're trying to get across with their data and what they're trying to get out of their data. Psychologists tend to be really interested in interactions above and beyond main effects, whereas it seems to me like biologists, at least the papers that I've read so far, seem more concerned with the effects of the main effects, so the effects of each independent variable on its own, than they are with the interaction. Like, I could be wrong. I'm basing this on a very small sample size of talking to a small number of biologists and reading a small number of biology papers, but that seems to be the case. And it is interesting, you know? I would love to like look more into that someday and see like what type of, how all different types of disciplines organize their interaction graphs. Yeah, the different it is super interesting to me. Orange and blue are correct covers for bar graphs with 2 colors. I support this. I'm glad. Kiki and boba graphs. By the way, Xenotime, I'm sorry. There are going to be red and green graphs coming up. I think I tried to make sure that the shades of red and green would make it so they're still colorblind friendly, but I sincerely apologize that we are changing the colors from the desirable blue and orange to red and green later on. My bad. The way like language influences thought in ways of independent of like the meaning of words but just the sound. Yeah, that's also interesting. The whole Kiki and both thing is so cool to me. Physics versus astronomers fight a lot since physics people want to see laws and associations, whereas astro people like seeing the raw data. I got involved in a fight over this. I think one of my first conversations with Phi was about that paper, and we were arguing, like, not like antagonistically arguing, but like friendly arguing over the best way to organize a graph for data with 2 independent variables. Because both of us had never once seen the way that the other discipline had done it before, so both of us were completely blindsided at how the other people were doing it. It was a bit of a ride. Like, I literally went into the paper and I reorganized the graphs to make them look what I was used to looking at. And I showed it to Phi. I'm like, isn't this easier to interpret? And he was like, no, I don't understand this graph at all. It was a very funny, like, cultural, disciplinary difference thing. Are linguistics and psychology related disciplines? I would say so. I don't think there's much communication between linguistics and psychology, but there's definitely a whole sub-branch of psychology that goes a lot into linguistics. And anecdotally, as a psychologist, I think linguistics are super interesting. And I think that we should collaborate with linguists a lot more. Most of the psychology work in linguistics that I'm interested in, or that I'm familiar with, sorry, and familiar is a very strong word for it, is related to language acquisition, so language learning. But there is that, I think you're kind of getting at something called the Sapir-Whorf hypothesis, which is the language that we speak and the way it's structured can change how we think. I think there's kind of mixed data on that. Yeah. Yeah, that's definitely something that people do study. I'm just not super familiar with it. Yeah, cultural differences across disciplines. I agree. It's a major barrier to communicating across disciplines too, though, which is deeply unfortunate. Like, I'm kind of lucky in that, like, the area of psychology that I'm in, or like my specialty, when I started in it, there wasn't a lot of work in it, so I was reading all over the place. I was reading whatever things on that topic I could get my hands on. So I wasn't just reading psychology, I was reading political science, and I was reading philosophy, and I was reading anthropology, and I was reading history, but like, that's not the norm. Usually people stay within their own discipline, and like, increasingly this topic has become very popular in psychology. So I've talked to Sai about it because she specializes in a disturbingly similar area to me, and she started on it later than I did, and it seems like she's mostly stayed on the psychology side of it because now it's just, there's a lot of it. The like critical learning window for language. Yeah, that would definitely fall under psychology. I've heard the word psycholinguistics at some point. That's a lot. That's true. Come to think of it, I have heard of psycholinguistics. You'd think I'd know about this because I do text analysis and linguistic analysis, but I haven't done really much with psycholinguistics at all, which is funny. Sapir-Whorf is a great plot for a sci-fi movie. Like, we're pretty sure, but it's not really a thing. But we're pretty sure it's not really. Yeah, there's some complicated things with Sapir-Whorf. Like, it's very, very difficult to test. I mean, like, lacking a word for something can definitely shape thought. That is true. It's more difficult to think about something if you don't have a word for it. On the other hand, though, if you can conceive of it, but there's no word for it, it's difficult to communicate that you are conceiving of it, which is a problem for testing that hypothesis, if that makes sense. I like bouncing around a bit. Chem one day, phys the next. Oh, hey, a cool CS paper. Yeah. I would love to be able to do that. The further advanced you get, though, the harder it gets because, like, I usually submit to psychology journals, so I need to do stuff that are related to psychology journals. Oh, hey, astro work time. I mean, like, the polyzyme thing I was yapping about in Phi's server. If that was in the biology channel, I admit, looking at the biology channel in Phi's server made me so confused, and I didn't know what was going on, and I muted it because every time I look at it, I felt very confused. It's... I'm deeply embarrassed to tell you this, but I have not looked at the biology channel on Phi's Discord for quite some time, which actually caused a problem because I sent Phi, well, not really a problem, but I sent Phi a thing and he's like, oh yeah, we're already talking about that. And I was like, oh, it was in the singular channel that on your Discord that I had muted. The lack of an adjective for the order of monomers is really strange to me. That isn't really... My eyes glaze over whenever I try and go through it. Very much a physics guy. Same, except me being a psychologist guy. Like, when I first joined the server, I really tried to keep up with that channel, but eventually my brain power just gave out. I think I need to watch Phi's streams more, and the more I watch Phi's streams, I think the more I'll understand. But also, when I'm not at work, my brain is mush. But when Phi explains it, like, when I watch his streams, I understand what's going on. But when I read that channel, everybody's talking at a much higher level than I'm at, so I'm just like, oh, I don't know what's happening. I'm probably doing, like, physical chem stuff, so all the physicists think I'm a traitor and the chemists think I'm a loser. It's funny how that goes. I have a friend doing math physics, of course, and he admitted to be fully unable to fully fit in with that. Yeah, that is a unfortunate problem in psychology. I kind of have that deal with, for a while there in grad school, I was sitting awkwardly between political science and psychology. And that was a little weird. But it wasn't, like, at least political science and psychology, we definitely don't do the same things and we use different methods, but in the grand scheme of things, we're fairly similar. We're not super different. Like, the way that we treat statistics and stuff and the way that we do do our studies is definitely different, but, like, it's not completely foreign, which is helpful. I felt like I had a place in both areas, but it can be weird being stuck in the middle sometimes. Like, my master's committee was like that. I was stuck between two very different schools of thought, which delayed my master's by a very, very long time. All right, sorry, I want to get through this because the pain is coming back. So I'm gonna keep going. Okay. So here's the graph of the data that we were just talking about. On the left, we have, these are the scores for people in public. On the right, we have the scores for people in private. The blue bars on the left are how many hard problems they got right. Orange bars. No, you're fine. I'm very easily distracted, Marlon. This is totally normal for one of these streams. Just unfortunately today I made some poor choices and ate something I definitely shouldn't have, and so I'm in a bit more of an urgent mood to finish the stream today and just go lie down. Don't be like me. Be smarter. We were less than halfway through the slides. It's okay, because a lot of the later slides are going to go by really fast. Like, I know that there's a lot of slides in this, but if you look at the later slides, like, we're almost to the point where we're going to start zipping through the slides crazy quickly, so I'm not worried. Yesterday in physics lab, I was told to put unused chemicals back in the container, which is a big no-no, but the TA was like, this isn't chem, nobody cares. Oh, no! Oh, no. Yeah, okay, back on track. Okay, so this is kind of neat. We can actually, by looking at this graph, if you get some practice, you can see the main effects and the interaction here. It does take practice, though. And again, it's easier to see here because we're assuming no sampling error. Oh boy, I've been there. It's okay, me too. I've been there. I've been there on and off for all of my life, so it's not like I'm not used to this sensation, you know? Like, this isn't bad. Like, I can emergency end the stream if I want to. I have had this happen when I was like out and about with no way to get home, or like, you know, when I was in the middle of teaching a lecture in front of a lecture hall. That's much worse. This is a good scenario, you know? Okay, anyway. So, main effects. First, let's talk about the main effect of whether it's in public or in private. The way that we can check this is these two bars are in public. Main effects only care about that variable. I only care right now whether you have an audience or not. So I'm going to average across the task difficulty. I don't care about task difficulty right now. And I can see the average number of problems solved in public is about 40. That's about halfway through the hard and easy for that. We've been informed to spam Psy if they suddenly vanish. Yeah, if I suddenly vanish, I am reasonably confident that Psy would be able to find somebody who could help me. Or Maury. I don't, well, if Maury's in this channel, if Maury's in the chat, that you don't even have to contact Psy. Maury will be able to help me, but, or like find somebody to help me, but if Maury's not here, Psy's a good second option. But hopefully it doesn't come to that. Okay. Anyway. No, I forgot that. I don't want to stress out Maury, though. They've got enough going on. Don't. It's okay, Maury. I'll be all right. But if I'm not all right, you would be able to find somebody. Don't drive over here, please. No, I'm seriously gonna be fine. I'm 99% joking. Don't you freaking dare. Okay, I need to keep going. We're gonna finish this lecture, and then I'm gonna get back to reading my webtoon, and I'm gonna lay down. Okay, so the average for public is about 40, and we can see the average for numbers right in private is also about 40. So assuming no sampling error, on average, people in the public condition and the private condition are solving about the same number of problems, indicating that there's probably no main effect of if they're in public or in private. How we feeling about how I'm sort of getting this average together of these two bars? Reign of Webtoon continue. It's true. I'm like 160 chapters in now. We're having fun. I was halfway through a chapter when I stopped to do the stream. I just accidentally glanced at my phone and I remembered, oh no, I want to get back to it. Okay. But yeah, so I'm just averaging together. I'm basically trying to, in my head, create a bar that only represents the mean in public, ignoring whether it was hard or easy, and then a bar that only represents the mean in private, ignoring if it was hard or easy. And those means are about the same. So this suggests to me that there is no main effect of audience. On its own, audience tells me nothing. To look at the main effect of task difficulty, I am going to try and estimate the average that people got right for hard problems and that people got right for easy problems. So I'm going to try, in ignoring whether they had an audience or not, on average, how many problems did people get right in the hard condition? So the midpoint between our two bars for the hard position is about here. I'd say roughly people on average got about 35 problems right in the hard condition. And then I'm going to do the same for the easy condition. Ignoring whether they had an audience or not, the midpoint of these two bars, if I average the two easy condition bars together, would be about here, about 45. The average of the easy condition bars is higher than the average of the hard condition bars. To me, that indicates that there is a main effect of difficulty. People were getting more easy problems right, because those bars are higher on average, and getting less hard problems right, because those bars on average were lower. So I can see the main effect of difficulty from that, and I can see the main effect of audience by averaging together those bars. And finally, I can also see the interaction. This one has a pretty obvious interaction. So remember, an interaction is when the effect of one independent variable changes depending on another. Using graphs for this looks like it would be really hard with 3 or more variables. Yeah, it can be hard with 3 or more variables. It depends on what you're looking at, but sometimes it can be easy to see. It depends on what type of interaction you have. It's easiest to see if you only have 2 variables, but it's actually not too much harder with 3 or more variables. No, actually, I was thinking of 3 or more levels. When you get 3 or more variables, it does become a bit of a pain. I had that, I was about to show you my dissertation results because I had 4 variables in my dissertation, and graphing that became a nightmare. But I can't show you that because that would, my dissertation's public knowledge, and so you shouldn't see that. But yes, 3-way interaction, anything above a 2-way interaction, graphing it starts to become a bit of a nightmare. Like if I had a 3rd independent variable here, I would have to have 2 copies of this graph, 1 copy for the treatment condition and 1 copy for the control condition. It becomes a nightmare. The number of graphs that you have when you have more than 2 independent variables starts multiplying. It's kind of wild. Hurst ternary diagram bar graph. I've never heard of that, but I wonder if you could like set up a 2x2 grid of bar plots where they rise out of the plane of the page. You know what? In the past, I have actually, I wanted to actually, I was doing, it was a 2-way interaction, but it was a 2-way interaction between 2 continuous variables, which is a bit more of a pain to graph. And I really wanted to just 3D print the total plane of the effect. I really wanted to do that, but I couldn't figure that out. But if I do it again, I figured out my local library has a 3D printer. So if I could just figure out 3D modeling, I would be able to 3D print a graph of my results. How cool would that be at the conference? Just use a thumbtack to stick the 3D print of my result graph to my poster or something. How cool would that be? That would be so neat. Oh my gosh. I wonder how 3D printing, I bet you could 3D print a 3-way interaction, actually. That would be really neat. Hey, Blinkus, Blinkus. Welcome. Most important part of science is spending way too long in latex making graphs look exactly like how you want them to. That's with me, but with R. How are holographic projectors these days? I don't know, but I don't think most conferences have the budget for them. Just use like HoloLive Hatsune Miku technology to project your graph. That would be pretty sweet, actually. I'm not gonna lie. I would love to do that. Like you get like a smoke machine in the room so that the light has ways to, or like smoky mirrors or however they, I don't know, it would be cool. Small units are probably much more affordable. Imagine like going into a conference talk and the speakers just like dragging up like a portable holographic display. Can you imagine? I would actually be delighted. I would be so pumped for that talk. I would make sure it was standing room only. Anyway. Wait, just give your presentation as a VTuber? Xenotime, no spoilers. No spoilers for future conference presentations, Xenotime. 3D world, you can have all the 3D graphs you want. It's true. That would be super cyber. Yes, no spoilers. That would be insane. It would be. That would be completely wild. Anyway, okay. So how can I tell there's an interaction from this graph? An interaction happens when the differences are different. So when the differences in one independent variable depend on the other independent variable. And we can see that here. There's a huge gap between easy and hard in the public condition, but there's no such gap in the private condition, right? I can see that difficulty matters in the public condition, but it doesn't matter in the private condition. That is the interaction. There's only a difference in my difficulty conditions in public. There's no difference in private. We can also look at this as a line graph, and I can see all the same things. I can take the average of the points in public. So this is just treating it as a line graph. The average in public is about here. That's the midpoint between my 2 public points, it means. The average in private is about here, and I can see that those are about the same. There's no main effect of difficulty. Or there's no main effect of audience. But for difficulty, if I look at the average of the hard line and the average of the easy line, I can see the average of the easy line is taller than the average of the hard line. That is my main effect of difficulty. People were doing better on the easy problems than they were on the hard problems. And finally, my interaction. You can tell there's an interaction on a line graph. Yeah, this is kind of how you saw the bar graph in your head. Yeah, I think a lot of people have an easier time looking at the line graphs than the bar graphs, but we tend not to do line graphs as much for this type of interaction because we don't want to imply that there's like a continuous variable here. These are nominal variables. It's not like there's a trend where scores are decreasing from continuously from public to private. It's tricky. We don't want to imply that there's like a continuous variable here, you know, like, so we typically don't present it this way, but I think it can be an easier way to think about it. And we do this when one of the variables is continuous. Anyway, we can see the interaction here. One way we can see it is there's a big gap in public, but there's no gap in private. That's one indication that there's an interaction. The other, though, if you have a graph like this and the lines are parallel, there's no interaction. If the lines are not parallel, like here, that indicates there is an interaction. That indicates the gap in one level is different than the gap in the other level. That indicates an interaction. So if they're parallel, no interaction. If they're not parallel, there is an interaction, probably. I mean, we still have to account for sampling error, but for now we're pretending sampling error doesn't exist. So let's get some practice. I've got a bunch of graphs for us to look at, and that's why this presentation is so big and like has so many slides. They're just yeah, most of them are examples. So you can have any combination of main effects and interactions. It could be that you have nothing. You fail to reject the null for everything. Neither of your independent variables does anything on its own, and they don't interact with one another. That would be no main effects, no interaction. You can have one main effect, so only one independent variable does anything, and no interaction. Or it could be that both of your main effects are significant, both of your independent variables do something on their own, but they don't do anything special when you put them together. You can also have zero main effects. Your independent variables don't do anything on their own, but when you put them together, they do something, like baking soda and vinegar kind of deal. Like if you just put them in bowls on their own, like nothing special is going to happen. But if you put them together, that's zero main effects and an interaction. Sometimes you have one main effect and an interaction. This was the example of the dust explosion that we went over at the beginning, and also the social facilitation. Only one of your independent variables does something on its own. The blah, 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 of course, blah, 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 is totally a scientific term. It absolutely is. Make sure you're spelling it right. It's the blah, 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 you know. Anyway, noting it down. Good, good. This is important information. I see. That is what you've been typing out all this time. That is welcome, Phi. Happy to have you. But yep, that's absolutely what I've been typing all. Actually, what I've been typing all this time is more like, you know. But is something different than you know. See, this is my specialty: verbal keyboard smash. It is my special attack. Oh gosh, I better start going quick. The pain is getting considerably worse suddenly. Can't wait till AI trains on your videos and has to contend with that. Yeah, good luck, AI. Whatever was in the food is getting to them. This is true. I'm gonna take a moment actually to just wince. Ow. Okay. Yeah, it's definitely getting worse. So let's I'm gonna try not to get distracted or go on tangents because ow. Okay. Maybe call it early and take care of yourself. But interactions, Marlon. Interactions are so good and important. Revving my engine. Maury, I swear to I will sick my cat on you if you come anywhere near here right now. I will sick my cat on you. He's ready to go. He's ready to attack you. Okay. So, you can have your independent variables doing nothing on their own, but they do something special when they interact. You can have one independent variable doing something on its own, the other doesn't, and an interaction. And you can have all of it. You can have your independent variables both do something on their own, and they interact. So I'm going to show you examples of all of these. And of course, I have chosen zombies and vampires. So our first independent variable is the type of undead you're dealing with. Are you dealing with zombies or are you dealing with vampires? Our second independent variable is the city this is happening in. You're either in Los Angeles or you're in New York City. And our dependent variable is casualties. Because I don't know. Look. Well, it seemed fun. It seemed like a silly, fun thing to do. So I'm going to show you both the table version of this with the means and then the graph, two versions of the graphs for each of these. Zero main effects and no interaction would be the average casualties for zombies and vampires are the same, so they're equally scary and deadly. The average casualties in LA and NYC are the same, so both cities were hit equally hard. So there's no main effect of undead. There's no main effect of city. The difference in LA for zombies and vampires was 0. Both were equally scary in LA. And the difference is also 0 in NYC. Are these like conversion casualties or full fatalities? I feel like when I'm talking about this I typically talk about it as if they're full fatalities. And in fact, I think on the graphs, the y-axis is actually going to say murders, which suggests that zombies are capable of murder, which suggests that zombies are capable of intent, which is a whole philosophical debate we could get into that I'm not going to get into now. But just think of it in terms of fatalities, I think would make the most sense. Oh, ow. Okay. I'm gonna try and power through. I powered through worse. Okay. We can also see, so like there's no interaction. The difference between zombies and vampires is the same regardless of which city you're in. There's no interaction. Graph-wise, it looks like this. We can see the average for LA is the same as the average for NYC. The average of our 2 zombie bars is the same as the average of our 2 vampire bars. And the difference between zombies and vampires is the same regardless of what city you're in. There's nothing happening here whatsoever. Here's the line graph version of it. 2 perfectly flat lines that perfectly overlap with each other. Nothing's happening. Nothing. No main effects, no interaction, nothing exciting. Next one. 1 main effect and no interaction. On average, zombies cause 60 fatalities, and vampires cause 50 fatalities. So we have a main effect of undead. Remember, we're assuming sampling error doesn't exist for now. We have a main effect of undead. Zombies were deadlier than vampires. The average of casualties in LA and the average of casualties in NYC was 55 in both. So there's a main effect of undead. Zombies were deadlier, but there's no main effect of city. Both cities hit equally hard. Is there an undeath control group? No, unfortunately, I don't have a control group here. And then finally, there is no interaction. Zombies were equally deadlier than vampires in both LA and NYC. In both cities, zombies killed 10 more people than vampires. So city didn't change the effect of undead at all. There's no interaction. And here's the graph. In LA, we can see the average in LA. So if I'm only looking at the city, I don't care about the type of undead. The average for the 2 LA bars is about here. The average for the 2 NYC bars is about here. So city, there's no difference in city. I'm not seeing one. I can see the main effect of undead. The average for the zombie bars is around 60 up here. The average for the 2 vampire bars is considerably lower. It's down here around 50. So I can see on average the zombie bars are definitely higher than the vampire bars. There's my main effect of undead. And finally, I can see there's no interaction here. The gap between zombies and vampires in LA is the same as the gap between zombies and vampires in NYC. So there's no interaction. Zombies are always deadlier than vampires regardless of where you are. As a line graph, it looks like this. Once again, we can see the average in LA is about the same as the average in NYC. The average of the zombie bar is higher than the average of the vampire bar, so there's your main effect of undead. And these lines are parallel. There's no interaction. The gap is equal on both sides. The lines are parallel. No interaction. Then we have 2 main effects and no interaction. The average casualties for zombies was 30, and the average casualties for vampires was 20. So, once again, we see a main effect of undead with zombies being deadlier than vampires. The average casualties in LA was 35, and the average casualties in NYC was 15. Now we have a main effective city. LA was hit harder than NYC. So we have a main effective undead. Zombies were deadlier. We have a main effective city. LA was hit harder. But we don't have an interaction. The difference between zombies and vampires in LA was 10. And the same is true for NYC. Yeah, there was a difference between the cities. Yeah, there was a difference between the undead, but zombies were always deadlier than vampires by an equal amount. Didn't matter which city they were in, zombies were always equally scarier than vampires. So there's no interaction. Here's how that graph looks. We can see the average of the two LA bars is up here around 35, and the average of the two NYC bars is down here around 15. There's your main effective city. LA got hit harder than NYC. Your average for the zombie bars, and again, we're eyeballing this, is about here, around 30. And then the average for our vampire bars is around here, about 20. So we can see on average, the zombie bars are taller than the vampire bars. And then finally, so that's our main effect of undead. And finally, the gap between zombies and vampires is the same in LA and NYC. The difference between zombies and vampires is the same in both cities, so there's no interaction here. Didn't matter what city you're in, zombies were always scarier than vampires by an equal amount. Here this is as a line graph. We can see, on average, more casualties in LA than in NYC. On average, more casualties from zombies, the zombie line is higher, than casualties from vampires. And we can see that the gap between zombies and vampires is the same size. These lines are parallel. There's no interaction. The city did not change how deadly zombies were relative to vampires. So those are all graphs where there are some variety of main effects, but there's no interaction. Now let's start looking at some significant interactions. And again, pretending that sampling error does not exist for today. Here, average casualties for zombie was 60, average casualties for vampire is 60. Average casualties in LA is 60, average casualties in NYC is 60. There's no main effect of undead. There's no main effect of city. Both were equally deadly, or both types of undead were equally deadly, and both cities were hit equally hard. But there is an interaction here. The difference between zombies and vampires in LA, 70 minus 50 is positive 20. In NYC, the difference between zombies and vampires, 50 minus 70 is negative 20. There's an interaction here. The difference between zombies and vampires changes depending on what city you're in. So here's this as the bar graph. We can see the average casualties in LA was about 60. The average casualties in NYC was also about 60, so no main effective city there. Both cities were hit equally hard. The average casualties for vampires is right about 60 as well. The average casualties for zombies, once again, roughly around 60, so there's no main effect of undead. Both of them were equally deadly on average if we ignore the city, but there is an interaction here. In LA, zombies were deadlier than vampires, presumably because it's sunnier in LA, and in NYC, vampires were deadlier than zombies. Presumably because vampires can dodge all the cars in NYC, and zombies can't. I don't know. So there is an interaction here. If you just look at the independent variables on their own, it looks like nothing's happening. But when you look at how they affect each other, it completely flips. I need to be more worried about zombies than vampires in LA, but I need to be worried about more vampires than zombies in NYC. Here this is as a line graph. Oh, the average in LA is about 60, average in NYC is about 60. The average of the vampire line and zombie lines are about the same, about 60, so no main effect there. But these lines are not parallel. They're not parallel. That indicates that this is an interaction. This type of interaction specifically is called a crossover interaction. It's when the effect of one independent variable completely flips depending on the other. Which undead is deadlier completely flips depending on which city you're in. This is a very desirable type of interaction to have. I think I've also heard it referred to as a disordinal interaction. Could be wrong. All right, let's look at one main effect and interaction. Average for zombies is 75. Average for vampires is 65. So there's your main effect of undead. Zombies are deadlier. For LA, average casualties was 70, and NYC, average casualties is also 70. There's no main effect of city. So there's a main effect of undead. Zombies are scarier. No main effect of city. Equally hit hard. The difference between zombies and vampires in LA was 20. Zombies caused 20 more casualties than vampires in LA. But there's no difference between zombies and vampires in NYC. They were equally scary. That's an interaction as well. We can see the average casualties in LA is about 70. The average casualties in NYC is also about 70. The average for zombies is around 75. The average for vampires is around 65. There's your main effect of undead. Zombies were deadlier than vampires. And finally, there's an interaction here. There's a gap between zombies and vampires in LA, but there's no gap in NYC. In LA, it does matter which type of undead it is. In NYC, it does not matter which type of undead it is. How we doing, by the way? We hanging in there okay? Things making sense? I hope. This is one of those skills that gets better with practice. So, you're following Yi? Oh, good. I'm good. I get it. Staying quiet, not to distract. Thank you, Marlon. I'm feeling better now, though. I'm feeling a bit better right now. So, I'm doing all right. I can go a bit longer if I need to. All right. Oh, and here's the bar graph version. Good. Yeah. I'm glad too. All right. We can see in the line graph version. Average for LA and NYC is about the same. Average for zombies is higher than the average for vampires. There's your main effect of undead. And these lines are not parallel. The gap between the lines in LA is much bigger than the non-existent gap in NYC. There's your interaction. The last one is what we saw with the social facilitation, right? Yeah, this is what we saw with social facilitation. We had one main effect and a significant interaction. So it looked something like this. There was gap in public, but there was no gap in private. Yeah. This is just the same type of interaction that we saw there. Good memory, by the way. It's a really good memory. All right. I've got one more. This is everything. Everything's significant. You've rejected all of the nulls. The average for zombies is lower than the average for vampires. So in this case, vampires were scarier. They were deadlier. The average in LA was lower than the average in NYC. So in this case, NYC was hit harder than LA. There is a main effect of undead. Vampires are deadlier this time. There was a main effect of city. NYC was hit harder than LA. The difference between zombies and vampires in LA is 25. The difference between zombies and vampires in NYC is -45. So there's an interaction here. The differences are different. And this is what that looks like. Some of these are going to be a bit harder to see because the differences are smaller. But the average in LA is around here. The average for NYC is a bit higher up. This one's a bit harder to eyeball. I would almost have to take a ruler or something. But the average casualties in NYC is a bit higher than the average casualties in LA. We can also see that on average, the zombie bars there are about there. And on average, the vampire bars are a bit higher. So there's your main effect of undead, vampires being deadlier than zombies. And we can see the interaction. Not only is the gap a different size in LA and NYC, So not only was there a bigger gap between undead and NYC than there was in LA, the direction of the gap flipped. Zombies are deadlier in LA, and vampires are deadlier in NYC. There's an interaction. Here's the line graph version of it. This, again, it's a bit hard to eyeball the effective city, but the mean for LA is a bit lower than the mean for NYC. And I'm sorry, it's a little hard to see here. And if you're looking at real data on a graph, it's not always going to be easy to see this. Sometimes it will be obvious, other times it'll be a bit harder to see, and you'll have to go into the results section and actually like read the statistics, you know? Like you can look at the graph. I find it's usually, what I like to do is if they have a graph of an interaction, I'll look at the graph, then I'll read the text to like see what's significant, and then I'll look at the graph again. And especially if I'm having trouble interpreting the graph, I will use the write-up of the results section to figure out what's going on in there. But it's always good practice if you're reporting an interaction to have a graph of it, because it can be really difficult to write these down. Anyway, we can see the vampire bar is on average a bit higher than the zombie bar. So there's your main effective undead. And finally, the bars are not parallel. This is an interaction. Not only does which one's deadlier flip, this gap is a different size. By the way, when I say lines are not parallel, that doesn't necessarily mean that the lines have to cross or meet on the graph. It could be that, like, the lines look like this. They don't meet on the graph, but they're clearly not parallel. That would still be an interaction. How are we feeling? How are we doing? Anything I can clarify? What if your graph is not in flat space? Yeah, that gets fun. There's a lot of ways that we deal with that. There are programs where you can generate a 3D graph. Typically, when your graph is not in flat space, that means you have more than 2 independent variables in my experience, or you have all your variables are continuous. You have 2 continuous independent variables and a continuous dependent variable. Those are the circumstances, at least that I've encountered, where your graph is not on a flat plane. There's multiple ways of dealing with that. You can graph it in 3D these days. Oh, good. Yeah, you can graph it in 3Ds these days. R gives some options for that, or like a graph that makes it look 3D. I've done this before with a technique called surface response analysis. It's really cool. Let me see if I can... Surface response analysis. Plot. And they have ways of like sort of... I wonder if I can find like... Is this open access? I don't want to share it if it's not open access. Figure available. Terms and conditions apply. What are your terms and conditions? Can I show this? Personal Maybe I can just draw one. I can try and draw one. Let me... Oh, I was making a joke about how parallel lines look different in spherical and hyperbolic. Oh, that's beyond me. So, I mean, you have a point, though. Like... But yeah, I overthought that. Response surface analysis, though, is cool. It graphs, like, if you, let's say you have 2 independent variables that are continuous and a dependent variable that's continuous. What it does is it generates, like, an image of, like, a plane that represents, like, oh, it arcs up, like, I'm having trouble drawing this right now. It's not going at the right angle that I want it to. Oh, the plane looks a bit like this or something like that. And it makes it look 3D, which is super neat. Or sometimes we'll, like, if you have a 3-way interaction or something like that, let's say I have undead, city, and time of year or something like that. Or undead, city, and time of day. I might end up seeing graphs that look a bit like... I might end up splitting it. So, like, I might have a graph like, here's day, and here's night. and then LANYC, LA. Yeah, garlic consumption per capita. That's going to get a bit more difficult because that's a continuous variable, you know? But yeah, you could do that as well. So it could be like maybe in the day in LA, zombies are much deadlier. At night in NYC and LA, vampires are much deadlier. Like, three-way interactions start getting gross. But yeah, are these mystic zombies or Revan? These are just like stereotypical zombies. They want your brains. They go real slow. They don't have conscious thought or anything like that. They're just boring. Salt lines, my worst type. I feel like salt lines, isn't that usually like more ghosts and evil spirits? I feel like zombies are just, I guess it depends on what force is propelling the zombie. I feel like I could go on like this for a while, and I'm feeling fine right now, but seeing as we're at the end of the presentation and I don't know when the pain's gonna flare up again, I should probably stop for now. Yeah, they did originate from Haitian tradition, but there's a lot of other traditions out there that have things similar to zombies that aren't zombies. So it's like, it's one of those things, it's like, there's a lot of different cultures all over the world that had things like vampires. So like I could go in forever about like different types of undead in different cultures and how a lot of cultures before they ever encountered each other, at least that we're aware of, they actually had different sort of monsters that are similar. Yeah, I'm sorry, this is distraction mode, but this is a topic that I'm very passionate about, and I do enjoy how most large bridges are non-Euclidean architecture. Ah, that sounds interesting. I just like the phrase non-Euclidean. I've seen some really screwed up architecture, by the way. Your voice is choppy, by the way. It just started. Oh, weird. I wonder why. I wonder why. Huh. Maybe that's my sign to stop. It might be just me, but it alternates on and silent. Not on my end? Oh, okay. Hyper Rogue is fun. It isn't for me. Okay, good. I was really worried for a second there. Sorry, Xenotime. But I mean, I probably should stop now. Like, I'm feeling fine right now, but I never know when it's going to hit me again. And also, I'm at the end of the PowerPoint. I'm done. So, like, yeah, thank you, Marlon. Thank you. Luckily, this doesn't seem like it's going to last very long. I should be completely fine by tomorrow. But, yeah, I think that's all that I have for you today. Thank you all so much for dropping in. Thank you for letting me ramble at you about interactions. Next time... Guess what we're talking? So next time is actually the last lecture that I have. You rejoined and it fixed? Awesome. But yeah, next time is actually the last lecture that I have in this series, which is exciting. It was Lovecraft didn't have the constitution for maths. That guy was a character. But yeah, next one is the last one that I have in this series for now. Maybe I'll add more later on. But for now, next time's the last one. And we're going to talk about the math part of Factorial ANOVA. We're not going to go too deep into it, but yeah, we're going to talk about the mathy bit and like considerations for following up a Factorial ANOVA and stuff like that. Oh, hello, Mr. Kibby. Mr. Kibby also knows that it's basically dinner time right now, so that's another reason I should probably duck out, but oh man, thank you all so much for joining me. Thank you so much for keeping me company on this journey and for letting me talk your ears off about interactions, which are my favorite thing in psychology, or in statistics. If you can survive whatever was in the food till tomorrow, you die on Pokemon Day. No way, I need to survive. I need to survive till the weekend, because isn't there like a Pokemon Go event this weekend? Like, I think there's a Pokemon Go event this weekend that I've been really looking forward to, and I've been playing the things so that, like, I've been completing the daily tasks so that I can get the things, the pass. So I need to survive until this weekend, at minimum. At minimum. But I guess if I do have to go, Pokemon Day isn't bad. They need to survive until they're done with the webtoon. That's true, I need to finish the webtoon, and then I need to finish the novel, and And then I have to go, I have a certain concert with a certain cool person to go to with certain cool people this summer, so I have to survive for that. You know, don't worry, I'm gonna be there. I have survived far worse food incidents than this. So I'll see y'all on the other side. I'll see y'all on this other side. I promise you that. All right, maybe I shouldn't promise you because I can't promise anything, but I'll do my best. Cool. It's cool to see you doing cool stuff. As a Civ major, I'm excited for having. Oh, thank you. And thank you for coming. It's good to have you here. Yeah, I'm not very excited about math, but I am very excited about statistics. Yeah, I'll see you next one. I'll see you next time. And I'm very excited. Once these stat streams are over, that means I can really get started on the rest of those charity stream awards. So we've got that moral licensing paper that we're going to read together. I get to do a video on To Your Eternity, which means I need to start watching that, and I need to make sure I have enough tissues to cry. I mean, if you die, it's not like we can be annoyed. The promise didn't hold. I give you permission to be annoyed. That way my social anxiety will allow me to survive because I don't want people to be annoyed at me, and that fear of people being annoyed at me will be so strong that I will survive anything. I love To Your Eternity. It's so good. I've heard so many good things about To Your Eternity, and it seems like a show that I would really, really love, but also I know it's going to make me cry. I know it's going to make me cry. You need to bulk order tissues though? Yeah, I sure do. I need to go buy some tomorrow. The secret to immortality. Yeah. The secret to immortality is really just the fear of letting people down. It really is. Oh man. Okay, anyway. Have a great night, y'all. Thanks for dropping in. Take care. Get good sleep when you do, or have a good day if it's the start of your day. Yeah, I will see y'all later. Bye! If you die, I'll be so angry. I'm not gonna die, Maury. And if I do die, I will haunt you. In a friendly way. Alright, anyway. Very excited for more licensing. I'm glad. Oh, thank you very much. Thank you. Okay, I should really head out now. My cat is also staring me down because it's just past his dinner time, so I need to feed the beast. Anyway, take care, y'all. Have a great, great night. Take care. Thank you all for coming. Bye!